Right. In the previous class, we stopped here. The use case in SD-WAN. We are going to see this one by one now. All these points are very important when we talk about SD-WAN. Number one, the critical application SLA. What does that mean, critical application SLA? We know that there is a protocol called BFT, which keeps on monitoring the path performance. And let us say we got these three paths. One of the path has got 10 millisecond latency. The other one has got 200. The other one has got 160. And then the loss, the first link has got 0%. Jitter is 5 millisecond. Internet is 4 loss, 4%. 10 millisecond jitter, 1% loss in LTE, and 10 millisecond jitter. So this is what the performance of the path that has been discovered by BFT. So one of the path which suits the policy will be picked. Let's say the policy is the path with less than 150 millisecond. Loss should not be more than 2%. Jitter should not be less than 10 millisecond. Let's say that is the policy that we have set. So to meet the need of the application needs path whose latency is less than 150 millisecond. So this is the best path then, MPLS. Latency should be, for our application, the policy that is set for the application to use the tunnel is 150 millisecond, less than that latency. Loss must be less than 2%. And jitter must be less than 10 millisecond. So definitely this is the path that WAN edge router is going to assign to that application whose SLA is 150 and 210. And it is done automatically. What if none of this path has got the SLA met? I just said that service level agreement for the application is 150, less than 150 millisecond, less than 2% loss, and less than 10% jitter. We have it. Yep, this meets the SLA. But what if none of this meets the SLA? What will happen? For that also we need to write a backup policy. So according to the backup policy, when the primary path didn't meet the SLA, the backup policy that you write will be considered. So we have to have a backup policy for every SLA. There should be a backup SLA, backup policy. If in case the SLA is not met and the primary path does not meet SLA, automatically the backup path can be used. So that is what about critical application SLA. Secondly, we have bandwidth augmenting. We can have bandwidths of MPLS and bandwidths of internet combined together for application if it is necessary. And the traffic engineering can be set to steer the application traffic over the combined bandwidth. Let me repeat. We can have, what I just said is, we can have the bandwidth of MPLS and bandwidth of internet combined together and have traffic engineering to steer the application traffic over this combined aggregated bandwidth, which is what called as bandwidth augment. In case if policy is not set, we can have active design, means both will be used. So that's about bandwidth augment. SD-WAN support bandwidth augment. Next is secured segmentation. Secured segmentation, you see, segmentation is like VLANs. I want you to recall what you learned under VRF and VLAN. VLAN helps us to isolate traffic. Secure segmenting also used to isolate traffic. For example, the traffic of the corporate user and the traffic of the guest can be kept separate. How? They will be put into different VPNs. See, every VPN in SD-WAN will have a database. Every VPN in SD-WAN will have its own routing information database. This is where I want you to compare to VRF. Every VRF will have a separate control plane, right? Separate routing table, likewise. Each VPN will have its own routing information database so that WAN edge routers can split into multiple routers by using different VPNs. Yep. So each VPN is a VRF, but here we don't call it as VRF, we call it as VPN. In MPLS, we learned that each VRF is a VPN. And each VRF is a router. Here we don't use the word VRF, we simply use the word VPN. So whatever you speak under the VRF topic, it's the same point. Segment, secured segmentation. You can have multiple routers by using different VPNs for different traffic. For example, as I said, for the corporate user, a separate router. For guest traffic, separate router. Because each VPN has got a separate routing information database. So different VPN, different routers. Different VPN, different traffic. This is what called as secure segmentation. Now, by default, customer traffic from one VRF will not go to another VRF. Yes. Even in VLAN, traffic of one VLAN will not be mixed with the other VLAN. They are totally isolated likewise. No information is leaked in between the VPNs in WAN edge routers. They're isolated. As I said, each VPN is a router. WAN edge router has got multiple VPNs, means multiple routers, and they are isolated to each other. So, in short, if I need to say, the secure segmentation provides us complete isolation in both control plane and the data plane. And the policy is applied on those VPNs. So VPN or policy aware VPNs. So the policies that we write knows every VPN and their control plane and data plane. That's about secure segmentation. Thirdly, regional secure parameter. See, in the early days, before SD-WAN, if I need to have a layer 4 to layer 7 inspection on multiple sites, I need to buy a firewall on each site. Every site should have an ASA firewall. See, the expenditure cost is high now. We need to buy firewall for every site, which is costly. This regional secure parameter helps us to do service insertion, using which the firewall services will be advertised into specific VPN from the database. So from a regional hub or from a database, when we advertise, what are we advertising? We are advertising the firewall services. Then the VPN traffic will go through the firewall for inspection. So what I'm coming to say is you no need to buy firewall for every sites. You can keep the firewall in one of the site, like hub region or a data center. When traffic goes from site A to site B, it'll go via site C, because site C has got, it's a hub region or it's a data center, so that they get inspected. So the service insertion is possible. Even though SD-WAN has got IPsec for providing security, we cannot do the layer 4 to layer 7 stateful inspection. That's why we need this type of service insertion. We advertise the firewall so that it can do layer 4 to layer 7 stateful inspection. We advertise the firewall, we insert the firewall into the fabric. Whereas in traditional way, it's not that easy. Here what we see is we have decoupled the original location of the firewall. The firewall need not to be there on every site. We have decoupled it. The security device is just getting inserted into the application flow. The firewall can be located anywhere in the network. And we can have this control plane or the data plane policy, which will steer the traffic through the site where the firewall is located so that there can be a D-packet inspection for that particular application traffic. Say for example, we have two VPN, VPN 10, VPN 20. VPN 20 needs inspection. Means any traffic that enters into VPN 20 needs inspection. Whereas VPN 10 does not need any inspection, any special service chaining, special services. There is no service insertion in VPN 10. So what VPN 10 does is it follows the standard path, standard VPN label as the application traffic goes from one side to other. Whereas this VPN 20, which needs inspection, now can be sent via the firewall using what known as service label. This one I use the word standard label, standard path. Standard label steers the traffic in a standard path. This has got a service label. A service insertion is done, firewall insertion is done. So according to the service label, the traffic will be steered. So the service insertion and service chaining is introduced into this new security devices in every location. We don't need to buy security firewall device on every site. We just insert the service, advertise the firewall service to the VPN, and the application that will be mapped to this VPN will be steered through the layer 4 to layer 7 inspection. Fourthly, the direct internet access. Traditionally, for the internet access, what the sites will do is all the sites will go to the central data center. in order to get into the internet. Sometimes this may result in a delay, latency. If a site needs an internet, there is no direct connection to internet in traditional network. If you have done MPLS layer 3 VPN or MPLS layer 2 VPLS, you will understand what I'm saying. All the traffic from the sites that wants to go to internet, they go to the head office, and from head office they get connected to the internet, which is going to increase the latency and delay. But today we don't need to do that. We have cloud. The growth of cloud is very big now. And we got software as service, SaaS. It has grown bigger now. So majority of the application endpoints are in the internet today. Then why we need to go through a data center? Why do we need to go through a head office, which is going to lower the performance of the application that we are trying to use? So we need to have a direct connection to the internet. We need to have a circuit, direct connection to the internet, so that we can leverage the design to get more optimal access to those applications that are in the cloud. Yes, in SD-WAN, the WAN edge routers, they will have a direct connection to the internet. They need not to go through some head office, some data center. So designated internet traffic can be used directly at the branch office or from the regional hub. Direct access. So we are no more going through the head office because it is going to decrement the performance. For example, if you have Office 365, Microsoft Office 365, which is an example for SaaS, SaaS, software as a service. Going through a head office to access Microsoft 365 will be actually increasing the latency. Direct access, using direct circuit to the internet from the edge is possible, is allowed in SD-WAN. From the edge device, we can directly go to the internet. And all the rest of the traffic that is not internet will be using the VPN of the SD-WAN fabric. Means those traffic that are going between sites. They will be leveraging the VPN that are available, and those internet traffic will go directly using the designated internet transport at the branch office. Sixthly, cloud on ramp or cloud express, cloud on ramp. So this is for those edge routers that has got more than one internet connection. More than one internet connection. This is much advanced than DAIA. DAA is just one connection to the internet. This is multiple connection to the internet. When we have multiple connection, we need to pick the one which is best for us. So to make a decision, an intellectual decision, the cloud on ramp, what it does is it will look for the performance towards that specific software. For example, in our example, we were saying Microsoft 365. Microsoft 365 is in the cloud, and from the site we have more than one connection to the internet, circuit to the internet. So the cloud on ramp will be looking for the performance, the real-time performance information, and the decision will be made. One of this path will be used for the traffic. So when we have two internet connection, one of those internet link can be used by the branch, and that one link is decided by this cloud on ramp. And the other link could be as a backup. So this cloud on ramp helps to define the topology. It can be like a hub and spoke, or it can be full mesh. You can go to a hub router and to a spokes router, or if two spokes router needs to talk, they can go through a hub router or they can go directly. So SD-WAN supports different type of topology, hub and spoke, full mesh. The default mode SD-WAN supports is full mesh. Right. So cloud on ramp is already over. I am already into another topic called, sorry, I didn't move this like here, topology. Cloud on ramp is simple. You measure the performance of the internet links, circuits, and cloud on ramp dynamically picks one circuit whose performance is better. Using that link, the internet traffic will be forwarded. And now what we are seeing is the network topology that SD-WAN supports. The default is full mode, but this overlay can be full mode or hub and spoke as per our policy. All the tunnels, when all the tunnels are up between the WAN edge devices, traffic can go from anywhere to anywhere. If that is your policy, then you need full mesh. But not every customer will have that policy. Customer to customer, it may vary. So, what do we see here in this picture? Our data plane is full mesh. but this is by default, when just out of box. Our data plane is going to be full mesh. And when the WAN edge router comes up, they will discover each other C-log. Every WAN edge discovers the other's C-log, transport locator, which are an attachment point on the transport. And then it builds the IPsec tunnel between them, which is always one hop IPsec tunnel to each WAN edges. And it's going to be a full mesh by default. But through the policy, we can shape the network, the overlay, according to the customer's specific requirement. We can have a hub and spoke design like this. So, like we saw in the previous slide, even though it is a full mesh like this, we do not want this side and this side to talk. So we don't advertise. Using OMP, we advertise root, right? We don't advertise anything over this link. Likewise, we don't advertise anything over this link and this link and this link. So what is left? What is left is this link only. So you got the hub and spoke. So if site A wants to talk to site B, our policies, it has to go via site C. On particular VPN. Not all traffic of site A needs to go via site B or site C. If it wants to go to site B, not all traffic, some application traffic you want it to go via site C. For the rest of the application, you may be willing to have the hub and spoke, so there will be direct connection. And physically, they're all connected, but logically, we can have hub and spoke or partial mesh. According to the customer's requirement, we can have it. You remember a few minutes before, we saw here a regional secure parameter. It's achieved through this policy. Let's say you have a firewall here in the site. Any traffic going from site A to site B need to be inspected. If you don't have any policy, no inspection, it can directly talk like this. But we don't want like that. We want it to go via site C so that it can be inspected layer 4 to layer 7, stateful. Inspection can be done. So what we do is we don't advertise any routes via this link. So according to router A, to reach WAN edge B will be via WAN edge C. So if the data plane tunnel have got hub and spoke design, we have reduced the meshing of WAN edge routers by positioning the hub on the top. See, we're talking about the WAN edge device. None of this are vSmart. It's WAN edge. So the spokes need this. This is also WAN edge, but this we want it to be a hub. This is another WAN edge. This is another WAN edge. We do not want WAN edges to WAN edge spokes to directly communicate each other, they have to go through the hub site. For that, we write policy, we steer traffic like this. So what I'm coming to say in short is, every VPN can have its own topology. From the same site, there can be another VPN which can have full mesh. So each VPN in a network can have its own topology, and it can have its own desired traffic through the VPN, through the pattern, forwarding pattern. So we can establish different topology per segment and create the flow as per the design requirement. So a VPN can be partial mesh, a VPN can be point to point, a VPN can be full mesh. You can have any type of network topology as the overlay as per your application demand. So usually the applications will take advantage of the shortest path and understand that every VPN has got its own topology, means we need to know that the topology are done as per VPN basis, and each SD and SD-WAN edge can participate in different topology. You may have a full mesh for some other application, but for this application you have hub and spoke. So VPN topology can be influenced by leveraging the control policy. So it's the control policy, the one that is going to filter some T-logs, as I was saying here in this picture. The site A this site 1 filters the T-log of site 2. When it filters the T-log, means it won't accept. The particular VPN don't accept this site 2's T-log. That's how we configure. And site 1, for that particular VPN, it is seeing this as the next hop, the T-log. And from here to here. Now you see, VPN topology can be influenced. How you define the topology? Different topology, hub and spoke, point to point, full mesh. It is by the control policy. By leveraging the control policy, by filtering some T-logs, in another word, by modifying the next hop attribute, we achieve different topology for VPNs. So when a policy is defined, when no policy is defined, it's going to be full mesh. As we saw earlier, any WAN edge can talk to the other WAN edge directly. It need not to go through another hub. You will be having full route information on every WAN edge. So each site can talk to the other side independently. When there is no policy. So when we have some policy that is going to affect the topology, such policies are called as centralized control policy. Centralized. So when you don't have centralized control policy, it's going to be full mesh. When we have centralized policy, centralized control policy, the operation on the routing and the transport locator information is going to be now as per the policy. So with the help of OMP, we are going to advertise. We know about OMP. Earlier we learned OMP is the one which is advertising this T-locks. So we will filter the T-locks. Information is going to be now as per the policy, centralized control policy. So this manipulation allows for the customization of routing decision. So sometimes the policies may have the same objective. So we create hub and spoke topology by either filtering the IP route or changing the next hop for the prefix. So what we can do is, for example, we saw earlier the hub and spoke design. We have this hub and spoke design topology, how the policy will filter the advertisement of route and T-log between the spokes, between site 1 and site 2. The advertisement is not done, the route advertisement or T-log. So it has to go through the data center, which is site 3 data center. That's what your policy is actually. It has to go through the data center site because that is where the default route is advertised on the spokes. So that is going to now push the traffic to the centralized data center. This is what we call this centralized control policy that drives the traffic this direction. Physically, there is a connection here. There are other tunnels directly between mesh topology between these two sites, but for this particular application, the policy is to go through the data center. So the OMP routes of the hub is advertised to site 1 and site 2 for that VPN. So the next hop is seen as data center 3 according to the OMP T-log address. It is not the other spokes, it is the hub. So vSmart don't allow this WAN edge to advertise the route directly to this WAN edge. vSmart controls it by using OMP, by filtering the T-logs for a prefix or for the application. So between the spokes, we do have data plane tunnels. because the spokes are learned, the TLOGs are advertised, but the control plane is not formed because the routes are not advertised through this OMP. Fine. And now, this is what filtering, we just saw this. vSmart control saying this WAN edge cannot talk to the other WAN edge directly, it has to go through the hub, something like that. So OMP, vSmart, TLOG, all these informations, all these are involved in deciding the topology. Now, here what we see is we see there are 3 paths, and we want application to use path 1 and path 2, and we do not want the application to use path 3. We don't want the path to use LTE. This is our policy. We want this application to use path 1 and path 2. And preferred path is MPLS, you see, preferred path is MPLS. And the backup is internet. See, we have this BFD probes that are running on every tunnel. On every tunnel, the tunnel that uses transport as MPLS, that uses internet as MPLS. So if I have 3 TLOGs, there's going to be a BFD running for each transport. For each tunnel, there is a probe that are sent on the tunnel. So when an application comes in, this WAN edge will look at the tunnel and the paths that satisfy the SLA, which is set for the application. Say an application is coming on online. It wants to use the transport. So WAN edge looks into the 3 tunnels that is available. One is internet, another one is via MPLS, another one is via LTE. So now it compares the BFD live status, and it see which one satisfy the SLA of that application, so that the traffic can be sent via that path. If no SLA is specified, we have 3 TLOGs. So the application now has got 3 paths available. So if you have policy, according to the SLA, one of the path will be given. If you don't have policy, the BFD performance is not going to be considered. It is going to see that there are 3 paths available because there are 3 TLOGs for the destination. As long as the tunnel is up, as long as we have the BFD telling that the paths are up, they're not down. And when there is no SLA specified, meaning when there is no policy said, SD-WAN will do ECMP. Because there are 3 TLOCs, it will hash the traffic. It will send the traffic via all paths. If all paths have got equal cost, that is the condition. So if you have multiple paths, and when you don't have SLA, when you have 3 paths, say for example, not multiple, let's be precise, we have 3 paths here, and there is no SLA. Here I have an SLA what? Only these 2 paths should be used, and in that, this should be the preferred path, this is the second preferred, this is not preferred at all. This is policy based. If you don't have policy, and when you have equal cost path, to reach the next hop, ECMP is going to be equal cost multipathing is what going to be the policy when you don't configure a policy. So when you have ECMP, you can expect the traffic distributed across the paths, all 3 paths. But when there is a policy, traffic is going to be directed as per the policy. Now, how ECMP works? In SD-WAN, how ECMP works? ECMP will combine the layer 4 and layer 3 information. It uses the layer 4 source and destination port number between the WAN edges, and also the source IP address and the destination IP address, and the protocol, and what is that called? In QoS we have DSCP. So using all this, ECMP will do the load sharing, distribution of load across multiple links. Let me repeat again. ECMP will use layer 4 source and destination port number, layer 3 source and destination IP address, not only IP address in layer 3, the protocol field, the DSCP field, and the ECMP hash. Hash key, which is helping to distribute the load across multiple links. It's called hash key, ECMP hash key. So using all this, even though you have multiple TLOCs, multiple next hops, it can use the hashing for ECMP with all these TLOCs, and it will use all possible links. All right. So when you don't have a policy, when there are multiple paths with equal cost, this is what will happen. And if you have policy, now you have 3 paths which satisfies the SLA. Let's say all 3 paths satisfy the SLA. Then what you can have is you can have a hierarchy saying this is the preferred one, MPLS. So if MPLS fails, then internet is the preferred one. LTE is not preferred. Traffic should not go via LTE. So you can have such policy. How this is achieved? To set this preference, color is important. So when you have multiple paths, which satisfies the SLA, I use the color to say I prefer this color MPLS, and I use internet color as a backup. So color is involved in this situation whenever you don't have whenever you have policy. Whenever you have policy and whenever we have multiple paths meeting the SLA, we use this hierarchy in preferring the paths. So using color, we can say this is what the first preferred transport, and this is what the second preferred transport, and this is what the third preferred, or this is what the one which we don't prefer. So here in SD-WAN, we don't choose the best of the worst. We have very clear, predictable, design-based path selection. Color is what involved here. But default is ECMP. You can also have a strict behavior. What does that mean? Anytime voice packet comes, you need to use only MPLS. What if that MPLS path didn't satisfy the SLA? Then you can simply drop no service to the link. I don't want to send voice traffic via the internet and have a broken voice, poor quality voice. So you can also have a strict behavior. You can control traffic with strict behavior. It's only one path, only this path. Check for the SLA. If it satisfies, use it. If not, no service. No service to another link. So what we have seen is we have seen different topology option that you can have. The default is hub and spoke. OMP is involved, vSmart is involved, route advertisement using OMP, the next stop is involved in deciding the topology. From the WAN edge, some may be having hub and spoke topology. Some VPN may be having point-to-point, some may be having full mesh. So it is per VPN. And we learned about all these 6 different use cases of SD-WAN today. What is cloud on ramp? Cloud on ramp is whenever we have more than one direct connection to the internet. The cloud on ramp measures the performance of each connection, each circuit, and puts the traffic in a circuit which has got good performance report, lively report. Taking the internet directly instead of going through the data center, which is going to increase the latency, taking the internet directly to the internet traffic directly to the cloud, to the internet, is what called as DIA, direct internet access. Regional secure parameter is creating multiple routers on the WAN edge router, so that each router is a VPN. Each router has got total isolation from other VPN. We can compare this to the VRF. Segment augmentation, secure segment is like service insertion. Firewall as a service, if you want to insert, you can do that. Instead of installing a separate firewall on each site, we decouple the physical firewall and we just insert it as a firewall as a service to a VPN. And the application that uses VPN will be going through those inspection, as the VPN is going to steer the traffic through the site that has got the firewall to inspect. Bandwidth augment, as I said, you can aggregate the bandwidth if you need. You can aggregate the bandwidth of multiple transport. We just saw, no, when we have multiple paths with same cost, ECMPs, that's how you can increase the bandwidth. That's what bandwidth augment is. And then we also saw critical application SLA, where you use BFD and check whether the SLA is met. The path whose latency, loss, and jitter is less than the SLA that can be used for VPN to take the traffic. Right. So we'll stop here. We'll continue the understanding of what is coming next. Is understanding of all these components of SD-WAN is what going to come next. All the core SD-WAN concepts are covered to the maximum extent now. We are going to get into components of SD-WAN in coming class. Components of SD-WAN for maybe next 2-3 classes. Components of SD-WAN in detail. Any question on today's class?
No, sir.
No, sir.
All right.